The tranquil blue marbles we often imagine floating in the void are the exception. Most of the cosmos is filled with chaotic, hostile environments that look like they are actively trying to destroy themselves. Take HD 189733b. Its serene blue exterior is the visual byproduct of raging supersonic winds tearing across the atmosphere at 5,600 miles per hour. This graphic shows how those winds drive a terrifying weather system. Silicate particles in the atmosphere condense and fall as molten glass, but the velocity of the storms forces the rain to arc completely sideways, shredding anything in path. At WASP 76b, the situation is even more extreme. Because the planet is tidally locked, one hemisphere permanently roasts under its star at 4,400 degrees Fahrenheit. The heat is so intense it vaporizes iron on the day side. Currents drag that iron vapor across the terminator line to the cooler night side, where it condenses and falls as heavy liquid metal rain. While sideways glass and molten iron rain seem like the peak of cosmic hostility, they merely serve as the baseline of terrible for our true subject. 750 light-years away, in the constellation Draco, the dragon, sits TRES 2b. This world is so severe, it makes the previous environments look like hospitable tropical resorts. It is a massive gas giant with a physical trait that challenges our understanding of light. It reflects less than 1% of the starlight hitting it. Discovering a planet that actively swallows visible light forces astrophysicists to reconsider how planetary optics operate under extreme stellar stress. TRES 2b is a hot Jupiter, a classification for massive gas giants that orbit with an aggressive lack of personal space. Compared to Mercury, which sets 28 million miles from our Sun, TRES-2b is parked just 3 million miles from its star. At this point-blank range, it suffers continuous radiation bombardment. Tidally locked, one hemisphere permanently roasts, while the other faces eternal darkness. This combination of point-blank proximity and locked rotation creates an inescapable thermodynamic death trap. We measure this darkness through albedo, or reflectivity. Earth reflects 37% of sunlight, and Jupiter over 50%. The best fit model for TRES-2b is just 0.04%, making it physically darker than a lump of coal or black acrylic paint. The 1800-degree heat instantly destroys reflective ammonia clouds, leaving the atmosphere unable to produce the bright stripes we see on Jupiter. Instead, the planet is swathed in a soup of vaporized sodium, potassium, and gaseous titanium oxide that actively swallows 99% of incoming photons. It isn't completely invisible, however. The blistering internal heat causes the planet to emit a faint, dim red glow. Because it absorbs so much energy, the planet re-radiates it as thermal infrared heat. To the human eye, it looks less like a world and more like a burning ember on an electric stove. There is a core scientific anomaly here. The known concentrations of sodium and titanium oxide cannot mathematically explain why the planet is this black. This missing data suggests the planet's atmospheric mechanics are operating outside our current chemical models. Mapping these hidden chemical makeups requires next-generation technology, like the massive golden mirrors of the James Webb Space Telescope. Solving the puzzle of this missing chemistry could change how we calculate atmospheric survival in extreme environments. Mapping these worlds provides a front-row seat to the literal limits of thermodynamics. Looking up at the night sky, we can be grateful that this specific red-glowing nightmare is 750 light-years away. Ultimately, understanding the galaxy's most aggressively hostile environments highlights the unique, stable climate we enjoy on our own nitrogen-oxygen world.